Amazing. So thank you all for joining. We have immense joy to have David Brown here to speak with us today. David received his PhD in physics from the University of Texas at Austin, working with Claudio Bunster and Mark Hanot. He then held postdoctoral positions at the University of Vienna, UT Austin, and the University of North Carolina, where he worked closely with James York. Since then, David has been a professor in the Department of Physics at North Carolina State University, and in 2010 was elected a fellow of the American Physical Society. David's research has spanned a number of topics in general relativity and quantum gravity, including in black hole thermodynamics and numerical relativity. Current interests include the extreme mass ratio in-spiral problem, which is to say predicting the motion of a small black hole or neutron star as it spirals into a large black hole. David is a creator of the YouTube channel Physics Unsimplified, which includes lectures on general relativity and various topics in classical mechanics, and recently authored an undergraduate textbook, Introduction to Scientific Computation, to be published soon by World Scientific. And we're really excited to hear about singular Lagrangians and constrained Hamiltonian systems. So David, please take it away.
Okay, thanks, Will. It's a real pleasure to be here. I love this topic. I just have lots of fun with it. And so I really enjoyed putting together this lecture. So let's jump in and see if I can get this. Yes, so first of all, just terminology. Singular Lagrangian systems are systems that have a mass matrix that's singular. The mass matrix, also sometimes called the Hessian. More precisely, it's the matrix of second derivatives of the Lagrangian with respect to the velocities. So that's a singular Lagrangian system. And when you try to put it into Hamiltonian form, it becomes a constrained Hamiltonian system. So these are the same, just the Lagrangian and Hamiltonian versions of the same systems, which are singular. This class of systems includes gauge theories. So for example, we have electromagnetism, Yang-Mills, the relativistic particle, string theory, general relativity. These are all examples of singular systems. And there's also various sort of idealized systems in classical mechanics that have this same property. And I've pictured a couple of them here. Throughout this talk, and I think the next talk, I'll actually focus on these simple examples in classical mechanics because I think it's a really good way to learn how to deal with these systems, to see it in a simpler context, simpler than general relativity or string theory and so forth. So I've already mentioned that these systems include gauge theories, which should tell you why it's important. But I'll also talk a little bit more about the history behind this subject and the motivation later in the talk. Okay, I want to jump in and start by just reviewing Lagrangian mechanics, try to establish some notation and terminology. Lagrangian is a function of the generalized coordinates, which I'll call q sub I, and also their velocities, which I'll denote q dot for the time derivative of the q's. And the index I ranges over however many values it needs to be, just depending on the number of generalized coordinates. Okay, from the Lagrangian, we can form the action. It's the integral of the Lagrangian. And this is a functional of q. In other words, S is a function of the functions, q of t. And we extremize the action with respect to variations in the q's with fixed endpoints. Okay, so the calculation looks like this. The variation in S, the action is, there's a term that comes from varying the q dots and a term that comes from varying the q's themselves. Now we want to integrate by parts to effectively flip this dot from delta q over to the factor in front of delta q. So that gives this term with a minus sign. When we do the integration by parts, of course, there's also a total time derivative term that integrates to the endpoints, and that's this term right here. Now, because q is fixed at the endpoints, that tells us that delta q is 0 at the endpoints. So this term is 0. Let me see if I tried to set this up so that I could mark on the slides as needed.
Yeah.
Yeah, there we go. So this term is 0. And we're just left with this integral term, and then setting delta S equal to 0 because we're extremizing the action. The usual argument is, well, in order for this to be 0 for all delta Q's with the condition that they're fixed at the endpoint, but otherwise arbitrary, in order for that to be equal to 0, then the quantity in curly brackets must vanish. All right, so quantity in curly brackets is of course Lagrange's equations, given right here. Okay, so if we unravel Lagrange's equations a bit by taking this time derivative, the quantity in parenthesis dl dq dot, that's a function of q and q dot. Okay, so we have one term that's second derivative of L with respect to the velocities times q double dot, and another term that's second derivative of L with respect to q dot and q times q dot. And then on the right-hand side, dl dq. Okay, just as a way of simplifying the notation, we can define the mass matrix, Mij. It's just the matrix of second derivatives of L with respect to the velocities. And then Lagrange's equations take this form. And in this form, it looks a lot like Newton's second law. In fact, it is Newton's second law in generalized coordinates. So we have mass times acceleration is equal to a bunch of stuff and this stuff just depends on the q's and the q dots. So this is the general force. Okay, so now if this mass matrix is invertible, then we can multiply through by the inverse of m and solve that equation for the accelerations. And the reason for doing this is because we want to ultimately interpret these equations as an initial value problem. So in other words, given initial conditions, the initial positions and the initial velocities, we want the future evolution of the system to be determined. Okay, and there are the various theorems in differential equations that tells you that, you know, a differential equation like this or a system of equations like this, as long as the right-hand sides satisfy, you know, certain nice properties, then the evolution will be determined and be unique. Okay, it will, you know, existence and uniqueness theorems. I like to think of this initial value problem in just very sort of simplistic terms. If I imagine doing creating a numerical code to solve this system of equations, I would discretize the time axis. So here's the time axis, time 0, time delta t, 2 delta t, and so forth. I would discretize the velocity at time 0. So now, given these initial conditions, q and q dot at time 0, we know this quantity, we know this quantity, and we can solve then for q at the first time step delta t. And now this next equation is just our system of equations with the left-hand side discretized. Okay, we know q at time 0. We now know q at time delta t. The right-hand side is just a bunch of q's and q dots evaluated at delta t, or we can evaluate at 0 if we like. So the right-hand side is determined, and we can solve this equation for the q's at time 2 delta t. And then we just go on from there. We just iterate this equation by bumping up all the time arguments by a single delta t and then solve for q at 3 delta t. So in that way, we just march forward. So given the initial conditions, the future evolution of this system is completely determined. All right, so all of that assumed that the mass matrix is invertible. Okay, what if it's not invertible? What do we do? Okay, in that case, we refer to the Lagrangian as being singular. Okay, before I get into singular systems, I want to just go through a non-singular example. So this is just the example of two springs connecting two masses. And the upper spring will have a stiffness or spring constant K1, and L1 is the relaxed length. In other words, the length of the spring when it's not compressed or stretched. For the second spring, the lower one, it has a stiffness K2 and a relaxed length L2. The masses are both M. And as generalized coordinates, I'll just use the distance of each mass from the ceiling. So X1 and X2 is shown in this diagram. All right, so this is just a picture again. So the first thing we do is we form the Lagrangian. As you know, the Lagrangian is just the kinetic energy minus potential energy. So here's the kinetic energy, 1/2 mv squared for the upper mass, 1/2 mv squared for the lower mass. The potential energy is just that's the potential energy in the upper spring, 1/2 k times the amount it's been stretched or compressed squared. This is the potential energy in the lower spring. X2 minus X1 is the length of the spring, and then we subtract the equilibrium length and square it. These terms are the gravitational potential energy of the two masses. Notice here we have a minus sign. That's because I'm measuring X down from the ceiling. This is really plus mgh, where h is the height above the floor. But because I'm measuring down from the ceiling, these coordinates X1 and X2, we have minus signs here. All right, so now it's straightforward. We plug into Lagrange's equations, and this is what we get. For the upper mass, it's just the mass times acceleration is equal to the force that the first upper spring exerts on the mass. This is the force that the lower spring exerts. This is the gravitational force. Likewise, for the lower mass, we have the force that the second spring exerts on it and the gravitational force. All right, now notice we can naturally interpret these equations as an initial value problem. We just solve for the accelerations, x1 double dot, x2 double dot, give initial conditions, the initial coordinates and velocities, and then let the equations take over. The equations take that initial data and evolve the system into the future. Okay. Now let's look at our first singular example. This is a system that I call the compound spring, and it's obtained from the previous example by just setting the upper mass m to 0. So I've removed that upper mass and just welded the two springs together at this midpoint. Well, I can't draw an arrow very well. Okay, so once again, x1 is the distance from the ceiling to the weld between the springs. X2 is the distance to the mass. And the spring constants are K1, K2, and so forth. All right, now the kinetic energy for this system is just 1/2 mv squared for the mass. We have potential energy. That's the potential energy in the upper spring, the spring number 1. This is the potential energy in spring number 2. This is the gravitational potential. Lagrangian, as usual, is T minus V. Okay, now when we plug into Lagrange's equations, this is what we get. Two equations, and of course there's no x1 double dot because there's no kinetic energy term for x1. And so these equations are fine, but we can't really interpret them as an initial value problem, at least not in a straightforward way, because we can't solve for the accelerations. So this is a system where the mass matrix, it's the matrix of coefficients of the accelerations, that matrix is singular. Okay, but as I say, the equations still make perfect sense. This first equation actually is a statement of Newton's third law. So if I just rearrange it, what we have here on the left is the force that the spring number 1 exerts on spring number 2. And on the right, we have the force that spring number 2 exerts on spring number 1. Okay, and according to Newton's third law, those should be the same. Okay, so what we can do is we can take that expression of Newton's third law right here and solve for either x1 or x2. I've chosen to go ahead and solve for x1, and we have x1 in terms of x2 and a bunch of constants here. And then we can insert this result into the second of Lagrange's equations to eliminate x1. Okay, and this is the equation that we get. Okay, and now we can solve for the acceleration x2, and the evolution of the system is determined, right? We solve this for x2, given initial data, x2 at the initial time and x2 dot at the initial time. We can solve this for the future evolution of x2 as a function of t. And then if we want to know what x1 is as a function of t, we just plug back into here. And by the way, this, of course, you'll probably recognize this is just the equation for a simple harmonic oscillator with an effective spring constant of K1, K2 divided by K1 plus K2. Okay, the key point here is that notice in this example, this singular example, x1 and x2 are not independent variables. And we say that the system is constrained. All right. Please speak up if you have any questions.
All good so far. Yeah.
Okay. Okay, so now let's review Hamiltonian mechanics. All right, for the first step in defining the Hamiltonian description of the system, we define the conjugate momenta as the derivatives of the Lagrangian with respect to the velocities. Okay, and after defining the conjugate momenta, we define the Hamiltonian. It's defined as PQ dot minus L. By the way, I think it's probably obvious in this day and age, but when I have a repeated index I, it's being summed over.
All good.
Okay, so now the action in Hamiltonian form is is the integral of PQ dot minus the Hamiltonian H integrated over time, and this is a functional of Q and P. And so now we can extremize this action with respect to Q and P, again with Q's fixed at the endpoints. So the calculation looks like this: delta S, we have a P times, from here we have a P times delta Q dot term, a Q dot times delta P term, and then there are terms coming from the variations of Q and P of the Hamiltonian. Okay, again, we want to integrate by parts to remove the dot from this delta Q. So the dot flips over to the P with a minus sign, that's this term. When we do the integration by parts, there's a total time derivative term that integrates to the endpoints, that's this term right here. And once again, because Q is fixed at the endpoints, this term is 0. Okay, and we're just left with what's in curly brackets here. Setting delta S equal to 0, we now argue that for that to be true for arbitrary delta Q and delta P, then the coefficients of delta Q and delta P must vanish.
Sorry, just one quick question. Where you have the variation of the Q dot, should I think of that Q dot as some function of Q and P, or is that really truly an independent variation, independent of the variation of Q's and the variation of P's?
No, well, it's independent of the variation in P, but not independent of the variation in Q.
Because the action above is only a function of Q and P.
Right. So in other words, it's a function of these functions. So if I put in a function Q of T and a function of P of T, I get out a number.
But I do think of P, I could think of P as a function of Q dot from the definition of P as the variation of L with respect to Q dot, right?
Yeah, but I'm ignoring that now. I'm constructing a functional of two independent functions, P and Q.
And saying, okay, P and Q are independent, and I can think about a time derivative of Q. I could think in principle about a time derivative of P if I wanted to.
Yes.
And those are independent of each other.
Right. That's right. So I'm going to actually come back to some of these points with a little bit more care in a minute.
Mm,
Because what you're pointing out is that this tells us that P is actually some function of Q and Q dot,
right,
right? But that's not what I mean when I'm writing this. Okay, so
right.
this P here is actually a different P than this P, right? Because this P down here is not a function of Q and Q dot.
Mm,
Okay, let me come back to this. I
mhm.
mean, these are the kind of subtleties that are glossed over in most, textbooks on classical mechanics, but it's important to get straight here.
Yeah, please
So
continue.
let me just go on. If you have more questions in a minute, let me know. Okay,
Mm,
so for now, treating the functions Q and P as independent, we vary the action with respect to Q and P, and we get this expression, and we argue that the coefficient of delta Q must vanish and the coefficient of delta P must vanish. Okay, and that leads to Hamilton's equations. Q dot is dH dP and P dot is minus dH dQ. Okay, and now we can easily interpret these equations as an initial value problem. We give initial values for the Q's and the P's, and then these are simple first order differential equations. The future evolution is uniquely determined. I can easily, again, I think of this very pragmatically. I can easily write a computer code to solve these equations for all time, given just this initial data. Um, and let me remind you or tell you that often we view the motion of the system as a trajectory in phase space. So phase space, here I'm just assuming there's only one Q and one P variable. So phase space is just two-dimensional. So each point in phase space represents the state of the system. And we start with some initial state at t equals 0. That's this dot here. And then these equations take over and evolve this dot into the future. So that's this curve, this trajectory through phase space. Okay, as an aside, before I continue, I want to introduce the Poisson brackets. This is just a nice way of sort of encoding the evolution and rewriting Hamilton's equations in kind of a slick way. Okay, so given a phase space, this space of P's and Q's, we can define the Poisson bracket in this way. So f and g are just any functions of P's and Q's. The Poisson bracket of f with g is defined as derivative of f with respect to q times derivative of g with respect to p. And again, there's a sum over this repeated index I, then minus the other way around. Okay, so for in particular, I can take f to be q and g to be q, right? And then I have the Poisson bracket of q with q. That turns out to be 0. It's easy to see because there's no p's involved, so these p derivatives vanish. Likewise, the Poisson bracket of p with p vanishes, and the Poisson bracket of qi with pj is just delta ij. Okay, and now with this notation of the Poisson brackets, we can write the time derivative of any phase space function f as just the Poisson bracket of f with h. And Hamilton's equations in particular can be written in this kind of slick way as q dot is the bracket of q with h, and p dot is the bracket of p with h. So the Poisson brackets just encode various derivatives of the arguments with respect to q and p. So um, there's nothing mysterious here. It's just another way of writing Hamilton's equations. Okay, so let's take a look at this non-singular example, the same one we examined before, just to see how it works out. We have two springs and two masses. This is the Lagrangian. We have the kinetic energy of the two masses minus the potential energy. That's the upper spring, the lower spring, and the two gravitational potential energy of the two masses. Again, the reason for even though we're subtracting the potential energy, there's a plus sign here because we're measuring the x's measure down from the ceiling. Okay, now we define the momentum variables. So P1 is mx1 dot, P2 is mx2 dot. The next step in constructing the Hamiltonian version of the theory is we construct the Hamiltonian itself, PQ dot minus L. So just plugging in and redefining everything in terms of X and P, we have this expression for the Hamiltonian. This is, you could guess this, right? This is just the kinetic energy of the two masses. This is the potential energy of the upper spring, lower spring, and the gravitational potential energy. So this is just the total energy of the system. Okay, Hamilton's equations. We take the Poisson brackets of the phase space variables with respect to the Hamiltonian H, and we find x1 dot is P1 over M, x2 dot is P2 over M. P1 dot and P2 dot are given by these expressions, and these are just, P1 dot, this is the force that the upper spring exerts on the upper mass. This is the force the lower spring exerts on the upper mass. And this is the gravitational force. And similar for P2 dot. Okay, so for this system, this is a perfectly regular system, non-singular, and we can interpret these equations as an initial value problem. So we give initial conditions, the x's and p's at time 0, and then let these equations take over and evolve the system into the future to give us a unique future trajectory. I keep emphasizing this this interpretation of our equations as an initial value problem, because if you think about it, we're deriving these equations typically from the action principle, and the action principle is really defining a boundary value problem, is defining a problem in which the freely given data are fixed at the endpoints in time, okay? But with an initial value problem, we want to reinterpret these equations by giving it all the freely specifiable data at the initial time. So there's some non-trivial sort of logical step there. And this will be important later on. Okay, so that's a singular example. But before we go on to a non-singular example, let's take a closer look at this transition from the Lagrangian to the Hamiltonian, because really the devil's in the details, as Will has already brought up some of these issues, some of the subtleties. Okay, what are we really doing when we define the momentum variables? What we're really doing is, well, remember that Lagrangian is a function of Q and Q dot. So partial L with respect to Q dot is some function of Q and Q dot. And let's call that function capital P. So what we're really doing is we're creating an equation like this, defining little p as some function of Q and Q dot. Okay, now in order to find the Hamiltonian, the first thing we need to do is we need to invert these relations. So we need to rewrite these equations by solving for the Q dots. We solve for Q dot as some functions of Q and P, and I've called those functions capital V, V for velocity. Okay, now once we've done this inversion, then we define the Hamiltonian. Actually, it's P Q dot minus L, but in more detail, it's P times Q dot written as a function of Q and P from this equation, minus L. L is the function of Q and Q dot, but in place of Q dot, we put this expression in terms of Q and P. Okay, so the big question is, can we do this inversion? Can we, starting with this equation, supposed to be an arrow. Yeah, can we do this inversion or not? Okay, and the answer is yes, we can do this inversion. Some basic theorems in functional analysis tell us we can invert this as long as this matrix, partial of script P with respect to Q dot, as long as that's not singular, then we can invert. Okay, but this matrix that tells us whether or not we can invert these relations, this is just the mass matrix, right? Because remember, P is just another notation for dl dq dot. So this matrix is the second matrix of second derivatives of L with respect to the velocities. And that's what we just called the mass matrix before. Okay, so if the Lagrangian is not singular, in other words, if the mass matrix is invertible, then we can construct the Hamiltonian version of the theory in the usual way. And the question that we're facing is, what if the Lagrangian is singular? How do we pass to the Hamiltonian form of the theory? Okay, I'll start describing the process for converting a singular Lagrangian system into a constrained Hamiltonian system. I'll describe that in a minute. Let me point out, though, first, there's a point here that is usually not discussed very carefully, I feel like. What we've established so far is that if you have a singular Lagrangian, in other words, you have a Lagrangian where the mass matrix is not invertible, that's equivalent to saying that you can't solve these equations for the q dots in terms of the q's and p's. So that, that we've established. But there's another consequence, and it's that there are constraints among the q's and p's. And if you look at Dirac's original work on this subject and many other people, they almost take this as being self-evident. And this is one of those issues that, just before we started the recording, I mentioned that I learned a lot of this way back in the 1980s, but still had some lingering questions. And this is one of the lingering questions, is how do you see that there must be constraints among the P's and Q's? Okay, and by the way, it's not hard to construct a proof of this statement if you make some simple assumptions like the Lagrangian is quadratic in the velocities. But that doesn't cover all cases because there are interesting Lagrangians that aren't quadratic in the velocities. So I've never seen a good argument for why there should be necessarily constraints among the phase space variables, the P's and the Q's. But I think everybody has some sort of argument that I think boils down to nothing more than the following. So the following is just an argument by example. So let's say we have an example with two coordinates, Q1 and Q2. So just two variables and two P's, right? Then this set of equations is this set of equations, where I just ranges over 1 and 2. And by the way, when I write this curly P1 of Q1 dot and Q2 dot, it's really a function of Q1 and Q2 as well, right? So these curly P functions are functions of all the Q's and all the Q dots in general. But I didn't want to keep writing, comma Q1, comma Q2 here. So we'll just let the Q dependence, the undotted Q dependence, go along for the ride. I won't show it in these functions. So just operationally speaking, how do you invert these equations for Q1 dot and Q2 dot? Well, the first thing you would do is you would pick one of the equations. Let's just say it's the first equation. It could be the second. But let's say we pick the first equation and we decide to solve it for Q1 dot. All right. And maybe decide to solve it for Q2 dot. It depends on the structure of the equations. It doesn't matter. Just relabel the indices so that it's the first equation that you're solving for Q1 dot. Okay. Solve this for Q1 dot. And what you have is some function I called capital V. Again, I use V because of the word velocity. Okay. So now you have Q1 dot as some function of P1 and Q2 dot from this equation. Now, the next thing we would do in order to try to invert these equations is insert this result for Q1 dot into the second equation. And that would give us an equation that looks like this. P2 is some function of V1, which is a function of P1 and Q2 dot, and also a function of Q2 dot. Okay, now, if the right-hand side of this equation, I just repeated it here. If the right-hand side of this equation actually depends on Q2 dot, what we do is we solve for Q2 dot. Now, I'm not worried here about, how hard that might be to do. I'll do it numerically if I have to. And I'll worry about if there are multiple roots, I'll worry about that later. But as long as this expression on the right-hand side actually depends on Q2 dot, then I'll solve this equation for Q2 dot. And that will give me Q2 dot is some function of P1 and P2, okay? And then we can take this result and we can insert it back into this equation to write Q1 dot as a function of P1 and P2. So now I've completed the inversion. I've succeeded in writing Q1 dot and Q2 dot in terms of P's. And also there's some floating around, there's some undotted Q dependence that I'm not showing. Okay, so that's fine, but we'd like to investigate the case where the Lagrangian is singular. We know when the Lagrange is singular, we can't solve for all of the Q dots in terms of P's and Q's. So that means we can't solve this equation for Q2. So as a result, the right-hand side must be independent of Q2. And this equation then is actually a constraint among the P's, and it's not the arguments, the Q's aren't shown in these arguments, but there are Q's also. Okay, so it just really kind of comes down to, in my mind, sort of proof by construction, that whenever you have a singular Lagrangian, you can't solve for all the Q dots. That means there must be some equations that are relating the Q's and the P's together with no Q dots. Okay, so as I say, this whole argument, this is something that occupies about one sentence in Dirac's book. It occupies one or two sentences in most textbooks on this subject. And I wish I had a really nice mathematical proof, but I don't. Any questions? Okay, so we have this chain of reasoning. If we have a singular Lagrange, yes.
One question about it.
If you have a constrained system, you don't necessarily get a singular Lagrangian. But if you have a singular Lagrangian, you have a constraints on your system.
It depends on what you mean by a constrained system. I mean, certainly I can have a Lagrangian system and I can have holonomic constraints. That doesn't mean it's singular, and you're right. It doesn't mean it's a constrained. It's different from a constrained Hamiltonian system. So the way the terminology is used here is constrained Hamiltonian system is precisely the Hamiltonian reflection of a singular Lagrangian system. But you're right. I can I can describe systems with holonomic constraints, and they're not constrained Hamiltonian systems or singular Lagrangian systems. Okay?
Yeah.
All right. So yes, so let's go ahead and look at this singular example of the compound spring where we welded two springs together and hung a mass off the end. This is the Lagrangian, the kinetic energy term, the potential energy terms. We define the momentum variables. So P1 we find is just 0 because this is Lagrangian is actually independent of x1 dot. P2 is m x2 dot. We can't invert these equations for x1 dot and x2 dot. And since P1 is 0, we say that the system is constrained. So this is the constraint among the P's and Q's that I talked about. It's very simple in this simple example. It's just P1 is 0. And this has some consequences, right? Not all states in phase space are allowed. We only allow states where P1 is 0. And that also tells us that not all initial data is allowed. So this is going to affect the way we interpret the initial value problem. But more to the point immediately, the immediate point is if we can't invert these equations for the Q dots, how do we find the Hamiltonian? It seems that we can't find the Hamiltonian. So how do we proceed in constructing a Hamiltonian version of the theory?
Sorry,
Of
maybe maybe a dumb question. So I suppose I try to construct H. So I say H is PQ dot, well, PI QI dot minus L. L here doesn't depend on X1 dot. So can I just take my P1 X1 dot and just say that that is 0 and my Hamiltonian is X2 dot P2 minus the L that's there?
Yeah, that's exactly what you do. So the answer is you just plow ahead and do it anyway. And it works. Okay, I'll get to that in a second.
Okay, great.
Okay. But it's not the end of the story. It works, but it's not the end. Okay.
Yeah.
So the procedure now for converting this singular Lagrangian system, any singular Lagrangian system, into a constrained Hamiltonian system was laid out by Dirac and Bergmann really independently in work that they did in the 1950s. And I refer to it as the Dirac-Bergmann algorithm. Some papers will just call it the Dirac algorithm. So there's various variations on those names and other names too. But I think Dirac and Bergmann are the main people who really pushed this forward. Okay, and Dirac's version of this story is summarized in a little book. This is less than 100 pages long, a book he wrote in 1964 called Lectures on Quantum Mechanics. And this version is also closely followed in a book by Hanot and Teitelbaum called Quantization of Gauge Systems. Now, Mark Hanot and Claudio Teitelbaum, Claudio is now Claudio Bunster. These were the people I worked with as graduate students in the 80s. So you can see they were interested in this subject in the 1980s. In fact, their interest culminated in this book in 1992. And most of the book is concerned with the quantum aspects of what you do to quantize these systems. But their first chapter is basically a review of Dirac's version of this algorithm. And I wrote a couple of papers a couple of years ago, and so a lot of what I tell you will be taken from these two papers. Okay, what was the motivation for Dirac and for Bergmann as well? Well, the motivation back in 1950 was quantum gravity. Okay, so if you think about what physics was like in 1950, theoretical physics, we had no string theory yet. No loop quantum gravity, none of these sophisticated approaches to quantum gravity. Path integral quantization was still very new. That was, Feynman, actually, I think it was an idea of Dirac's, probably from the 1930s, but Feynman kind of developed the path integral approach in the late 40s, but it was still kind of new and very formal. So in 1950, there was still hope that gravity could be canonically quantized. And the canonical quantization procedure says you start with the system in classical Hamiltonian form. You replace the phase space variables with operators. So they become operators in some Hilbert space. And in particular, the Hamiltonian becomes an operator. You replace the Poisson bracket, which I introduced earlier, with a commutator bracket with an IH bar thrown in for good measure. So this is now a commutator between operators. And Hamilton's equations, which look like this for general function on phase space. Hamilton's equations become the time evolution in the Heisenberg picture in the quantum theory. So that's sort of the in a nutshell, the canonical quantization procedure that seems to work okay for very simple systems. And of course, here it is 75 years later, and we don't know how to make it work for more complicated systems like general relativity. But at any rate, back in 1950, it was recognized in some way or another that the Lagrangian for general relativity was singular. It was not something that you could treat or convert to a Hamiltonian theory in a straightforward way. And in fact, the Hamiltonian form of general relativity wasn't really nailed down and understood until really the 1960s, primarily the work of Arnold, Desser, and Misner. Really, they're the first one to really understand how to put general relativity into Hamiltonian form. So the backdrop of all this is that people, Dirac, Bergmann, and others, wanted to quantize gravity, but they needed to first understand how to put it in Hamiltonian form. Okay, so let's take a look at the singular example, this compound spring. Okay, we start with the Lagrangian, which is a singular Lagrangian because there's no x dots in there, and apply the Dirac-Bergmann algorithm. So I'll explain the algorithm by way of this example. Okay, so here's the Lagrangian I just repeated. And each step in the algorithm I've just labeled 1, 2, 3, and so forth. And there's a bunch of steps. It goes on to many slides. Okay. So these first 3 steps are basically what you would do for any theory. Okay, you first define the momenta as the derivatives of L with respect to the velocities. Okay, and that defines some functions of Q and Q dot. So in our example, these are the equations that you get. Next step is, as I've already discussed, since this system is singular, you cannot invert the mass matrix. There must be constraints among the P's and Q's. Okay, in this example, and we call those constraints the primary constraints. Okay, and label them. There may be many of them, so I have an index here. So there's a bunch of functions of P and Q that have to vanish. Okay. In our simple example, there's only one function, only one primary constraint right here. Primary constraint is P1. So P1 has to vanish. Okay, the third step, this is what we were talking about a moment ago, is to just blast ahead and construct the canonical Hamiltonian anyway. Even though you can't invert, in the singular case, you can't invert these equations for the Q dots in terms of Q's and P's, you go ahead and construct the Hamiltonian in the usual way, and this is referred to as the canonical Hamiltonian. So the reason this works is there's a very subtle argument that was recognized by Dirac that this expression where we have taken these functions of Q and Q dot, which are supposed to be P's, and we take those functions times Qi dot minus L. This combination depends on Q dot, but only depends on Q dot through the combination that we call capital P. Okay, so the argument is if you vary this canonical Hamiltonian with respect to the Q's and the Q dots, so this is just some function of Q and Q dot. This is the result that you get. And you'll notice that there's no delta Q dots here. Well, there really are. There are delta Q dots buried in this delta script P. But the point is that all of those Q dots appear only in this combination script P. Okay, so for that reason, we can conclude that this canonical Hamiltonian is really a function of script P and Q. And so now we just substitute everywhere we see script P, we just substitute little p. Okay, and that gives us our canonical Hamiltonian. All right, so again, just to summarize, the upshot of this argument is that despite the fact that we can't invert these definitions of the P's for the Q dots, we can still construct a Hamiltonian. Okay, and in this case, the Hamiltonian is just P2 over 2m plus these potential energy terms.
Not sure that I fully understand the statement that the variations in Q dots are always sort of contained in the variations of your script P. Is it that they always come in combinations that are sort of the form of script P, or could you maybe elaborate on that more?
I can try. I'm not sure how to say it any better than I said it before, or that you just said it. I mean, this is, remember, we're varying this function with respect to Q and Q dot. Okay. And so you ask yourself, where are the Q dots in this expression? Well, they're buried in here, and I can expand this out. I could write this delta P as partial P with respect to Q dot, delta Q dot, plus partial P with respect to Q, delta Q. Okay, but that sort of defeats the purpose of this argument, because I want to show that all of the variations in the velocities are only appearing in this combination that we call capital P.
Is that it always moves in just a particular unified direction, right? It can't jump into a wrong direction. It's a bit like when you think about a tangent space or something. You know,
Yeah, I think there's some way of describing it that way and geometrically, and people, yeah.
Yeah, I think
So as I said, this is one of these subtle points, and this whole business is full of these subtle little arguments that I think for Dirac, everything was obvious because he was, but for the rest of us, it's a little bit of a struggle. I find this argument really funny because there's a Q dot here. So I tend to want to say intuitively that, well, the canonical Hamiltonian depends on Q dot. There it is. But that's not really the argument. It's varying H. Oh, the only way in which H varies because of variation in Q dot is through this P combination. All right, so as somebody already recognized, it's fairly easy for this simple example, for this Lagrangian, it's fairly easy to see that this is all going to work, because, you know, as soon as we write, wonder if I can, you know, if we just write naively, H is equal to, sorry, I have a little drawing pad, but I couldn't get it to work, so I'm having to use the mouse here. So we have PI QI dot minus L. You can see what's going to happen here. We have a sum over I. The P1 X1 dot. So we don't know how to solve these equations for X1 dot. We can't, but it kind of doesn't matter, right? Because P1 is 0. So P1 times X1 dot just goes away. So somehow magically, all the things that you would think are problems, like I can't solve this for these equations for X2 dot, it doesn't really matter because the constraint protects you anyway.
And here it's actually explicitly geometrical because it's absolutely flat, right? Easy to imagine opposite geometry.
Yes. This subspace P1 equals 0 is pretty easy to imagine. It's just the flat, as you say. Okay, so we can always construct the canonical Hamiltonian. And this is what it looks like for our simple example of the compound spring. And now the next step in the Dirac-Bergmann algorithm is to construct what's called the primary Hamiltonian. So that's H with the subscript P. So that's just the canonical Hamiltonian. And we add to it multiples of a linear combination of the constraints. So there's a sum over this index A, assuming there's more than one primary constraint phi. Okay? So, and these coefficients, these lambdas, are referred to as Lagrange multipliers. So for our example, this is the primary Hamiltonian. It's the canonical Hamiltonian, which is everything up to here, plus Lagrange multiplier times constraint. Okay. Now, these lambdas, these Lagrange multipliers, these are named because they're named Lagrange multipliers because they're analogous to Lagrange multipliers that you use for holonomic constraints in classical mechanics. They're not exactly the same because holonomic constraints are constraints among the Q's only, whereas these primary constraints involve the P's. But they're given the same name, Lagrange multipliers. And they're also, they play a role dynamically in the theory, right? So if we can form the primary action, which is just PQ dot minus the primary Hamiltonian integrated over time, and we consider that action, the primary action, to be a functional of Q's, P's, and the lambdas, these Lagrange multipliers. Okay, so we can vary this action and set it equal to 0. If we do that, the variation with respect to the P's gives us Q dot equals Poisson bracket of Q with HP. Variation of the action with respect to the Q's gives us P dot equals Poisson bracket of P with HP. So these are just Hamilton's equations for this Hamiltonian HP. And we also vary the action with respect to the lambdas, the Lagrange multipliers. And that gives us the constraints. Okay, so this is all fine. And at this point, I think there's another subtle point to be made. So I just want to ask the question, are we done? Our goal, remember, was to put the theory into Hamiltonian form. So let me go back. So is this Hamiltonian form or not? Well, we're not quite done. And let me explain why using this example. Okay, if we write out those equations for our example problem, the compound spring, we have x1 dot is lambda, x2 dot is P2 over m, and so forth. And varying the primary action with respect to the Lagrange multiplier, we get the constraint, the primary constraint, P1 is 0. And I just want to emphasize, these equations are correct. There's nothing wrong with them. And you can stop here if you like, but there's a problem with interpreting these equations as an initial value problem. Okay, and the problem is this. This equation, because it comes from an action principle, again, the action principle defines a boundary value problem, and it tells us that each of these equations must hold for all time. Okay, in particular, this constraint equation must hold for all time. Okay, so if we're going to interpret these equations as an initial value problem, how do we assign initial data? Well, naturally, you would think, okay, I'll choose my P's and Q's initially, arbitrarily, except that I better make sure that they satisfy this constraint. Okay, so I'll choose my P's and Q's initially with the proviso that P1 is 0. Okay, and then I'll let these equations take over and evolve into the future. The problem is these equations do not guarantee that this constraint will hold in the future. And in fact, what you see from this equation for P1 dot is that P1, even if P1 is 0 initially, it's not going to remain 0 whenever the right-hand side here is not 0. So the fix in this simple example, the fix is pretty obvious, it seems. We just want to also say that the right-hand side must be 0. Okay, but then really logically speaking, we have to be careful because we need to be careful to ensure that if the right-hand side is 0 initially, that it remains 0 in the future. And so maybe there's other conditions that have to be taken into account. Okay, so as just a system of differential equations, the equations that come from the primary action are perfectly fine and correct physically, but they don't allow for a natural interpretation as an initial value problem. Okay, so this is what I just said. Even if we restrict the initial data so the constraint is satisfied initially, the constraint will not necessarily hold in the future.
sorry, maybe and if I'm screwing everything up, we can just plow ahead, but, so we had the canonical Hamiltonian, which didn't have this addition of the Lagrange multipliers. Could we not have varied the canonical action, set that equal to 0, and have some equations of motion that we could solve?
Well, no, because we would have, if we had not had the Lagrange multipliers in there, we would have had 0 for x1 dot. Then what would have happened if we actually did what I said, if we actually went in and said, okay, P1 is 0 initially because I choose it to be 0. In order for P1 to remain 0, I have to have this combination equal to 0. And then if I use the equations of motion for x1 dot, x2 dot to check whether that's always 0, I'll find it's not always 0. And in order to make sure that it always remains 0, I need to have this function available here. So,
Got it.
right, so it actually, yeah, it actually wouldn't work.
Right, so you patch up.
But it does work for the primary Hamiltonian,
Right, gotcha.
for the primary action. Okay, so I think of it this way. In addition to choosing initial data so that the constraint is satisfied initially, we really have to choose initial data so that at the initial time, phi dot, phi double dot, and so forth are 0. Okay, so this leads us to the next step in the Dirac-Bergmann algorithm, which are referred to as consistency conditions. So what we do is we take the primary constraints, which I'm calling phi sub a, and we compute using the Poisson bracket and the primary Hamiltonian, we compute the time derivative of each of these constraints, and we set those time derivatives equal to 0. And we then investigate the consequences and what can happen for each of these equations. So this is some set of equations, one for each value of the index A. All right, so for each of those values of the index, we can have 3 different things can happen. One is that, well, it could turn out that the time derivative is 0 anyway, so we were all worried about nothing, right? So phi dot is 0. And by 0, I mean 0 when the constraints hold. So as long as the constraints are already satisfied, then we don't have to worry about this particular one being satisfied in the future. That's the first possibility. The second possibility for this equation is that it places a restriction on the Lagrange multipliers. Okay, so this is some equation that can involve lambdas, and maybe it tells us that lambda has to be some particular function of the P's and Q's. The third possibility for this equation for each value of A is that it's a relationship among the P's and the Q's. So in other words, it places another restriction on the P's and Q's. And in that case, in this third case, we refer to these restrictions on the P's and Q's as secondary constraints. Now remember the terminology, the phi's are the primary constraints. These are now secondary constraints, and there may be several of them, so I'll put an index M on here. So I'll denote the secondary constraints as psi sub m. All right, so now we have more constraints than what we started with. We have secondary constraints. And now we need to make sure, in order to interpret our system as cleanly as an initial value problem, we need to make sure these secondary constraints hold into the future. So we're going to iterate this whole process with using the secondary constraints, right? We compute the time derivatives, and then for each value of this index here, there are 3 things that can happen. Either psi dot is 0 anyway, we didn't have to worry, or there's a restriction on the Lagrange multipliers, or the third possibility is there's more restrictions on the P's and Q's. In this third case, we refer to these restrictions on the P's and Q's as tertiary constraints. And in general, there may be many of them. Okay, so obviously, I'm going to keep doing this, right? I'm going to then impose the consistency conditions on the tertiary constraints, and keep going on and on and on.
But it's interesting that you calculate the time evolution based on the primary Hamiltonian, which only is adjoined with the primary constraints. You don't add the secondary constraints to the primary Hamiltonian.
That's exactly right. And that's exactly one of the little subtleties that I never got straight until I went back and looked at this subject a few years ago. I was always confused. Was it the primary Hamiltonian? Because we're going to introduce more Hamiltonians down the line. But this part of the procedure, which I'm referring to it as imposing consistency conditions, this part uses the primary Hamiltonian in all of these steps. The primary Hamiltonian only includes the primary constraints.
Because it seemed like with the canonical Hamiltonian, you were arguing that we can't use that for time evolution because we don't have enough degrees of freedom to ensure that the constraints are consistent. But now we have the primary Hamiltonian, which has the same number of Lagrange multipliers as primary constraints, but we're potentially generating secondary constraints. Is there something that guarantees for us that we have enough degrees of freedom with just the Lagrange multipliers multiplying the primary constraints such that we can always ensure that the secondary constraints stay zero for all time?
Okay, so, well, I don't know. I mean, there are, by the way, there are people that write whole books on this subject, right? And they might be able to tell you the answer. But I think that ultimately it comes down to the fact that, if we go back to to this system of equations that come from the primary Hamiltonian, this system of equations is, I guess the assumption is that this system of equations is physically reasonable and self-consistent. Okay, and this system of equations only has the Lagrange multipliers that coincide with the primary constraints. Okay, and what happens in practice is that if you look at this consistency condition process, you could, in principle, as you go through, gather more and more restrictions on the P's and Q's. But if this system is self-consistent, then this is the only lambda you need to use. The one associated with the primary constraint.
Okay, thank you. Yeah, that's nice.
I don't know how to give a better answer than that. But you see, these equations
You
are,
also have a limited number of variables around, so right, you cannot have the number of constraints explode beyond the things you can hope to constrain.
Right.
Unless
that's right. And that's why, you worry that this process of imposing consistency conditions will go on forever. But in fact, it can't go on forever if you have a finite number of degrees of freedom, because it's got to end some point. Unless your theory is so weird that you have no dynamics at all, in which case maybe everything is constrained.
Yeah.
But
But
the process has to end.
Yeah.
So what's strange about these equations is, because each of these equations hold for all time, there are lots of implications, in particular for this constraint to hold for all time, that it imposes a lot of, well, we already saw it imposes I can take the time derivative of this equation, right? P1 dot has to be 0. That's how I conclude that the right-hand side here has to be 0. But also P double dot has to be 0. So I could take P double dot here, compute the time derivative of the right-hand side, then replace the time derivatives of x1 and x2 with these. That has to be 0. And I can just keep going on and on like this. But as long as these equations are, in any sense, self-consistent, physically reasonable, then all I need is the single Lagrange multiplier. Or said more generally, all I need is those Lagrange multipliers associated with the primary constraints. So that's sort of I guess a poor man's way of saying why we just use the primary Hamiltonian in each of these steps, no matter how deep we have to go. Again, these things are, like I say, this very well could be explained in some books on the subject, but it certainly wasn't explained in Dirac's writings. Dirac just made it seem like everything was obvious. Okay, so let's for our example, we've already said you can already tell how it's going to work out. This is the primary Hamiltonian. This is the primary constraint. This is just repeating for your benefit the Poisson bracket. The consistency condition says that phi dot, or in other words, phi bracket with the primary Hamiltonian, should vanish. If you compute this, you get this expression. So this expression is just our Newton's third law once again, right? So this expression must vanish. This is a secondary constraint, and it's our Newton's third law condition. So in the Hamiltonian form, we have primary constraint, P1, secondary constraint, this Newton's second law expression. And now we have to do it again, right? We have to check that the secondary constraint is consistent. Okay, so here's the primary Hamiltonian, here's the secondary constraint, psi. We impose consistency for the secondary constraint, and we get this expression. And now this expression involves the Lagrange multipliers, so this falls under the category of a restriction on the Lagrange multipliers. So here's the restriction, this expression. Okay, so what do we do next with all this? And now the consistency process has terminated, right? There's no more constraints to make sure they're consistent. Okay, so the next step in the Dirac-Bergmann algorithm, this is up, if you're keeping count, this is up to step number 6. We define what's called the total Hamiltonian, and that's just obtained from the primary Hamiltonian by incorporating any restrictions we have on the Lagrange multipliers. Okay, so the primary Hamiltonian, the total Hamiltonian, HT, this is the canonical Hamiltonian that I just underlined. And this is the lambda times primary constraint term, and I've replaced lambda with that restriction on the Lagrange multiplier, this expression. Okay, and now step number 7 is what we want to do is we want to take all of the constraints that we've gathered in our theory, all the primary, secondary, tertiary constraints, put them all in one group, and then reclassify those constraints as being either first class or second class. The first class constraints I denote with a C for constraints, FC for first class, and there's an index alpha just because there may be many of them. Okay. The second class constraints I denote as C second class, SC. The first class constraints have the property that they have vanishing Poisson brackets with all of the other constraints. And by vanishing, I mean vanishing when the constraints hold. So in other words, the Poisson bracket of any first class constraint with any other constraint has to be typically a linear combination of constraints. So things that are zero anyway. Okay. Now, this distinction is important because it turns out it's the first class constraints that generate gauge transformations. Okay, so these are first class constraints. They have vanishing Poisson brackets with all other constraints. Second class constraints are those that aren't first class. All right, if we look at our example, we have two constraints, phi and psi, and if you compute the Poisson bracket between the two, what you find is the result is K1 plus K2, which is not 0. So that tells us that both phi and psi are second class because they do not have vanishing Poisson brackets with each other. Okay, so in our example, simple example problem, both these constraints are second class. There aren't any first class constraints, and there's no gauge freedom in this simple model that we've been studying. Okay, so what I'm going to do is I'm going to continue to finish working out this particular example with no first-class constraints. And we'll look next time at the next lecture, I'll look at some examples that do have first-class constraints and gauge freedom. Okay, so the next step, actually, even if there are first-class constraints, this is the next step, is, although a lot of these steps are optional, right? It just depends on the form you want the theory to appear in. The next step is to define what's called the Dirac bracket. And the Dirac bracket is a replacement or an improvement, if you will, on the Poisson bracket. Okay, so the Dirac bracket is defined as follows. You take, form a matrix out of the Poisson brackets of all the second-class constraints. Okay, and I just call this matrix script M. This is not the mass matrix. This is just some other matrix, M for matrix. Okay, and then the Dirac bracket is denoted with a little star here. The Dirac bracket between two phase space functions, f and g, can be defined in terms of the Poisson bracket as, well, just the Poisson bracket minus this expression, which is, you know, Poisson brackets of f and g with the constraints, the second-class constraints, and we have sandwiched between them the inverse of this matrix. Okay. Now this bracket, again, Dirac proved all these things. It has good properties like the Poisson bracket, like it satisfies Jacobi identity and so forth. It has the important property that the bracket, the Dirac bracket with the star, of any function with one of these second-class constraints always vanishes. Okay, and this means, again, subtle piece of logic here that experience sort of shows why it makes sense. We can set these second-class constraints equal to 0 anytime we want to in working with the theory, as long as we commit ourselves to using the Dirac bracket. So if you think about what this means, so in our example, we have one of the constraints is just P1 equals 0. Okay, so imagine computing a Poisson bracket of P1 with, say, Q1. Poisson bracket of P1 with Q1 is 1. Okay, it's just the number 1. So even though P1 is 0, the bracket of P1 with something else is not necessarily 0. So that means we have to be very careful about using these constraints to rewrite or re-express, for example, our Hamiltonian. Okay, because it makes a difference whether we set these expressions equal to 0 before or after computing brackets. When we use the Dirac bracket, we can freely set these constraints equal to 0 anytime we like. And in particular, so here this is the statement. We can use second-class constraints to eliminate some variables. So for example, with the total Hamiltonian, we can eliminate some of the variables by solving these second-class constraints for some of the variables and substitute again. If we do that substitution, what we get is what's called a reduced Hamiltonian. And I'll denote that by H sub r. Okay, and then we can express the time evolution of our system as just by taking Dirac brackets of any function on phase space with the reduced Hamiltonian. Okay, so, pardon?
Also reduced phase space with stuff eliminated that.
Yes. Yes, this will give us a reduced phase space.
Making a
Okay.
smaller rolling mass.
So here's the example problem. This is the matrix of Poisson brackets of the constraints. It's this matrix. Here's the inverse of that matrix. And here's the Dirac bracket of any two functions on phase space, just written in terms of the Poisson brackets. If we look at the Dirac brackets among the phase space variables, x1, x2, p1, and p2, these are the only ones that are non-vanishing. x1 with p2 is some combination of spring constants, the k's. x2 with p2 is 1. All of the other brackets, like x1 with x2 is 0, p1 with p2 is 0, and so forth. Okay, so now with the Dirac bracket, we can eliminate some of the variables. We can reduce the phase space. So we can use these constraints to eliminate, for example, x1 and p1. Remember, phi is just p1, so there's not much choice but to solve that for p1, right? So p1 equals 0, and for the other constraint, psi, it was this Newton's third law expression involving x1 and x2. So I actually have a choice. I can solve it for either x1 or x2. But here I've chosen to solve it for x1 as a function of x2. And now we can reduce the Hamiltonian by substituting these expressions into the total Hamiltonian. Okay, when we do so, this is the result we get. And just to emphasize, there's nothing magic about my choice here to eliminate x1 and p1. I could just as well decide to eliminate x2 and p1. Okay, so here's x2 solved as a function of x1, and this would be the reduced Hamiltonian in terms of the leftover variables, which are p2 and x1. Okay, so both of these reduced Hamiltonians are perfectly good reduced Hamiltonians. Either way, either one, I get the following equations of motion using Dirac brackets. x1 dot is this combination of k's times p2 over m. p1 dot is 0. x2 dot is p2 over m, and p2 dot is this expression. Okay, and with these equations of motion, now we can choose any initial data that satisfies the constraints. Just any P's and Q's, we do need to make sure they satisfy those constraints. But once we do, then we can let these equations take over, these Hamilton's equations take over and evolve the system forward in time. Okay, so we have a nice, clean initial value problem.
Your constraints are automatically 0. The time evolution is automatically 0 from the Dirac bracket.
Yes, the time, as long as you start with the constraints satisfied in your initial data, then they will remain satisfied, guaranteed by these equations. That's basically the whole construction was designed to guarantee that those constraints will remain satisfied in the future. So once we satisfy them initially, we don't have to worry about them anymore.
Well, unless you run into numerical issues, right? If something gets a little unstable numerically, but
Yes, precisely.
of this as an exact procedure, you should be safe.
As an exact procedure, you should be safe. Yes, this was a problem in numerical relativity for a while, is start the initial data on the constraint surface, so to speak, satisfying the constraints, but then the future would drift away because of numerical errors and become uncontrollable. Yeah. Okay, so these are the equations of motion for a simple example. And yes, to bring it back to this sort of geometric picture, we refer to the constraint subspace of phase space as the constraint surface. So that's just the surface where the constraints hold. It's some subspace of phase space. For the simple example I've been using, phase space is 4-dimensional. But one of the dimensions is kind of trivial because it's just P1 equals, it's the P1 direction. Everything in this example takes place in the P1 3-dimensional plane of phase space. So I've suppressed P1 in this picture and just shown X1, X2, and P2. And this is then the constraint surface, this little plane here. And I also worked out with Mathematica some of the phase space trajectories, and they're just circles here. So we start with some initial data, some initial point here, and then those equations of motion I had on the previous slide just evolve the data forward. All right, so I think that's where I want to stop now. I've gone quite a bit over an hour, so but this is laying a good foundation. Next time we can get into first-class constraints and gauge theories. And I'll talk about this system, or maybe if I can get movies working, I'll show you a little movie of this. This turns out to be a classical gauge theory, a classical mechanical system, which is a gauge theory. That's it. Thank you very much for listening, and let me know if there are questions.
So I have to say this example turned out to be prettier than I expected it to be.
Yeah, I like this example very much. It's very simple, and it's described in one of my papers, but I actually used a different definition of the generalized coordinates. So I used x1 is the distance from the ceiling to the weld, and x2 is the distance from the weld to the mass. And that actually is kind of mathematically more interesting because it mixes up some things a little bit in a little bit more interesting way, but it's a little more confusing too. So, I mean, if you haven't seen it before, so.
Super. There were lots of questions during the talk, but we have some more. Bryce, go ahead.
Yeah, thank you. It was quite interesting. So I'm just curious, you mentioned singular systems, we're working classically now, and at one point you mentioned quantum mechanics. So what's an example of a singular system in quantum mechanics that's not, GR or, and sort of on that note, this Dirac-Bergmann algorithm, does it translate easily into quantum mechanics where you just replace the Poisson brackets with a normal commutator?
Well, yeah, I gave up trying to understand quantum mechanics a long time ago, so I'm not an expert. I'm not an expert on this, and I think that the canonical quantization procedure. I'm not sure. One of you can tell me, but I'm not sure it ever really worked much beyond a harmonic oscillator or some very simple.
Well, you can do it for electrodynamics, right? And then A naught is the thing that has no time derivative. And you can go through this game, but this is clearly a gauge theory, so it gets a little bit more complicated. I remember watching people try to do this in QCD context of light cone quantization and asking the question, where does the vacuum disappear to? And it hides in a constraint that you treat in a too simplistic way if you do it naively, but okay. So that gets complicated very quick.
Yeah, I think somehow, yeah, I have a colleague who works on light cone quantization, and I think to hear him talk about it, it seems like this could apply somehow. But
so it kind of that links to inverting P minus, so to speak, as a differential operator.
right.
And that's where all the non-trivial vacuum things disappear if you don't do this properly. So you can go for versions of Dirac bracket there. This was papers by, well, it's ages ago, by Vanna, Heinzel, and a couple of other guys from Regensburg. That's where I saw this when I got my master's.
Okay. It would be interesting, actually, I think, to take one of these simple systems like what I've described and just try to quantize it. I don't know. I don't know what would happen.
Yeah, I mean,
I think really. Yeah, I don't know.
And I think you would be very interesting because I think with the coupled masses, if you take it as M1 and M2, then as long as M1 and M2 are both non-zero, it's a non-singular system, and you should be able to solve it completely using sort of bog standard quantum mechanics and take the limit as say M1 goes to 0 and see if you get the same results as say the Dirac-Bergmann algorithm and replacing the Poisson bracket with the Dirac bracket.
Yeah, that almost sounds like a student problem that you could throw it into a bachelor thesis or something.
Maybe a third year project.
Yeah, actually, Yeah, well, that does sound very, well, yeah, this is interesting. I mean, I hadn't really thought of following up on all these things, but
I mean, the really nice thing about these mechanical examples is that it's an infinite playground, right? I mean, it doesn't throw all the complications of quantum field theory at you. You might actually get away with sneaking your way past the theoretical complication to unravel how the theoretical complication actually works.
yeah, I think that's what to be honest, that's what I feel like maybe my most interesting contribution here is to show some singular systems that come from the world of classical mechanics. If you look in books like, for example, Hanno and Teitelbaum, there are lots of simple examples with finite degrees of freedom, but they're always unphysical.
Yeah.
Have no physical basis at all. And then when they go to, you know, the bulk of their efforts is treating field theories, right? So, and then you get into lots of other complications, as you say, with
No
field
way they're
theory.
rushing ahead. I mean, I like your attitude here quite a bit. This is absolutely it's absolutely pretty.
Daniel,
I have a very sort of bare bones question. I feel like if I thought it through, there might be a better answer. But does anything in the sort of structure, the symmetries change when you do this? If you're thinking about something like Noether's theorem, you know, you are changing around what actually exists in your Hamiltonian, or potentially moving things around in your Lagrangian. Do you break anything or pick anything up? I'm not sure if you would, because you're only really changing your derivatives, but I'm not.
Well, if
I'm
that
not convinced
happens,
of that.
if that happens, you might actually change the nature of the theory of the way, right?
Well, that's what I'm.
Yeah, I think that, yeah, if you're doing things right, you shouldn't change the nature of the theory. If it has a symmetry, it should still have a symmetry.
well, I think
But I do think that people have people have written papers on Noether's theorem and constrained systems and so forth, linking all these things together. I believe. I'm just not, I don't know enough about them to comment, but
I think that's the whole idea of BRST quantization. So what I mean,
yes.
the Hanno and Teitelbaum book is a beast, but my sense was, okay, so I have some system with a gauge symmetry. I would like to fix the gauge. Now, by fixing a gauge, I'm breaking the gauge symmetry. Is there some way that I can restore that symmetry? And I think that's what BRST is doing for you. So in fact, you recognize that your theory is more than just gauge symmetric, it's actually supersymmetric. And then choosing a gauge would in principle break that but the way that you choose that gauge doing the BRST procedure preserves the supersymmetry. And so then you kind of get your cake and eat it too, with the pain conserved via the extra particles and the fictitious particles with the wrong statistics. But so maybe that's
Yeah,
also, yeah.
I used to know all that stuff. Well,
Uh,
just because Claudio and Mark,
yeah.
I was around when they were formulating all this BRST quantization and so forth, but it's been so many years since I've looked at it, I can't remember exactly how it goes. I know there's lots of ghost fields and things in the
Right.
path interval and yeah, but it was all designed to handle gauge theories, and they were coming at it from a Hamiltonian point of view, which so all this Dirac Bergmann stuff was sort of the foundation of what they were doing.
Right. Good.
Yeah.
Any last questions? David, you've exhausted us, which we deeply appreciate. Thank you so much for taking the extra time.
Okay, well, I'm sorry I took so long, but
No. This is
Yeah,
fantastic. We
it's
really
good.
appreciate it. So let's thank the speaker one more time. Yeah, fantastic. And